Today and Thursday. Next week is your turn. This project's going to count a lot for your grade. All right? So this is important, this project. And part of your grade will be based on your presentation and your attendance. I say that because I know some of you will have a tendency to come the day you're supposed to present and maybe blow off the day you're not presenting. So that's not a good idea. First of all, it's not kind to your fellow students. And I am going to keep track of who's here, and so that's important. So 2 PDF slides sent to Jisoo by Friday. You have 2 minutes to present, so I would really recommend you practice. Now, if you're in a team of 2 people, you could either, if you want to do a tag team presentation where you each do part of it, that's fine, but you better practice, make sure you can do the switch over pretty quick. Or if you want to pick one team member to do the presentation, that's fine as well. There will be prizes. Prizes, all right? How's that for an incentive? Attendance is required, and listen, please try to be on time. Good timing. Because we have a lot of presentations to get through, and there's always technical problems. You know, when you set up talks, things don't go right, something goes wrong. So we really have to get things moving quickly. So please try to get here on time next week, Tuesday and Thursday. Well, you should try to be on time every day, but it's especially important next week. Then the final project is due on May 2nd. Okay? 8 pages, NIP style. Okay, any questions about this? It'll be a lot of fun. There'll be some snacks too, yeah.
What kind of prizes are available?
Well, I'm not going to tell you that ahead of time. But let me just say, you'll be really happy if you win the prizes.
How are you going to select the winner?
How am I going to select the winner? The TAs are going to choose. Pressure's on, Jisoo, yeah. Can you bribe them? Yes. The TAs do accept bribes. Just kidding. Okay. Any other questions? All right, good. So last few topics, we'll see what we get through. I want to talk about random projections, then some random matrix theory, maybe a bit of differential privacy. I'm not sure what order to do them in yet. We'll see. But first I want to start with some random projection stuff, which is a continuation of our dimension reduction. So far we've talked about linear things like PCA and multidimensional scaling. Then we did some nonlinear methods. But there's another type of linear method. This is page 21 I'm on now, Random Projections Part 1, which is to stick to random things, but to do it, to stick to linear things, but to do it randomly. So when is this useful? So frankly, I think it's really useful when you're talking about very high dimensions. So sometimes you're dealing with tens of thousands, maybe even millions of dimensions. And you need some fast, easy way to reduce it down to, say, a few hundred dimensions or even 1,000 dimensions, something like that. That's probably when this type of thing is most useful, although it's a very active area of research. So it might be useful for even lower dimensional things. It's not clear yet. This is sometimes called sketching. And it's kind of amazing that it works. So the Johnson-Lindenstrauss theorem, which is what we're going to talk about today, it's the proof you'll see uses elementary concentration of measure that we've already talked about, of course. And the result is really quite amazing and almost puzzling, I would say. It's kind of unexpected. It's not a complicated result, but the result is kind of unexpected. So let's say what the problem is. So we're dealing with random vectors, x1 to xn, and they're in Rd. So we're imagining, again, D is quite large. And I want to map it somehow into Rm. So m is going to be smaller than D. This is our dimension reduction. So the way we're going to do it is really interesting. I'm going to take a random projection matrix. So this is going to be a matrix S. It's going to be an m by d matrix. And the way I'm going to construct this matrix is just fill it with random normals. All right, so each element, Sij, is just normal 0, 1. And when we do matrix multiplication, that's a linear operation. So we're going to be taking it into a lower dimensional space. We're actually just going to need to rescale things a bit just to keep them on the same scale. So we're going to define this mapping, L of x, which takes any point x. And all we do is do matrix multiplication. So we multiply S times any point x. X here is any point in our D. And then just to make things scale right, it turns out we need to divide by root m. So let's see, let's just check that this has the right order, right? S times x. So this is m times d. This is like a d by 1 vector. So the result is an m by 1 vector. So indeed, we have sent it to a lower dimensional space. So the first thing to notice is how easy this is, right? There's no optimization going on or anything like that. Just construct a random matrix, multiply it. And in the CS literature, there's a lot of work about even making this faster and more efficient, because matrix multiplication itself takes a bit of time and so on. So I'm writing it down mathematically. In practice, it can be done in very, very efficient ways. So this is really simple and efficient.
So
And
each point we use the same matrix.
The same matrix, correct, on each point. And the amazing thing is, what we're going to see is that the dimension that we're going to reduce down to is going to be about log n. I'll give you more detail in a minute. Okay, so that's pretty remarkable, because first of all, it's only logarithmic in the sample size, but do you notice something? The original dimension d never appears in this formula. This is what's remarkable about Johnson-Lindenstrauss. And the goal, yeah.
We're going to reduce, don't we pick m here?
No, m is the dimension we're reducing into.
But we generate the matrix S, right?
No, so we're going to decide what dimension m to go down into. Then we're going to generate this matrix. I'll tell you more about m in a few minutes. Okay, but the procedure couldn't be simpler. And what's the guarantee we're going to want? We're going to want to preserve, in some sense, pairwise distances. So the assumption here is that that's what we care about. And we've seen that that's come up before, like with multidimensional scaling. So the assumption is that we want to preserve approximately the pairwise distances. And if I call yi to be L of xi, what we're going to see is, what we're going to guarantee with high probability is that the following equation holds. For all pairs of data points, I and j, we get with high probability the following guarantee. So that the data reduction, the pairwise distances in the data reduction, are within 1 plus or minus epsilon of the original pairwise distances for all ij with high probability. And so let me now tell you the catch. There's an epsilon squared here. So if epsilon's small, this could still be pretty big, right? And that's why I'm saying it's mostly useful when the starting dimension is quite big, because you want to make sure this is only useful if the resulting m is much smaller than d. So that's our goal today, is to do this in detail. This is our first goal, at least, to do this in detail, and we're going to prove that this actually works. In fact, to be a little bit more explicit, we're going to take m to be 32 times log n over epsilon squared. So the way this works is you decide what accuracy you need, then you plug it into this formula, and this gives you an m. And if this m is much smaller than your original d, then you go ahead and do this. Okay, and there's lots of variations on this and improvements and so on. This is just the basic algorithm we're going to talk about. Okay, so we're going to go ahead now and get into details. Let me just make sure that the general goal is clear. Is everybody with me? Any questions?
How does it compare with our last Buddhist lecture?
Well, how does it compare, with like, say, the PCA and MDS and so on? It's giving a different type of guarantee. See, what was MDS doing? It was saying, given a certain dimension, find the linear projection which minimized the distortion of the pairwise distances, but it never said how much it distorted them. This is saying, given that you want to preserve it by a given multiplicative constant, this is how you project it. So it's giving a different guarantee.
What is the strange result that you mentioned?
The strange result, what seems strange to me, is that the required m doesn't depend on the original dimension d. Right? So if I told you I have n points in a 10-dimensional space or whatever, you can figure this out. But if I tell you it's in a 1 billion dimensional space, it doesn't change m. The original dimension doesn't matter. I find that a surprising thing. When you first see this, to me, this seems very surprising.
Does the choice of the norm matching matters here?
Yes. So if we didn't use Euclidean norm, there's a whole other set of methods you have to use that are a little bit more complicated.
So I'm just trying to wrap my head around this because it is really bizarre that
Yeah.
but it seems like maybe in some sense it kind of does, really depending on, I guess, the effective dimensionality of the data, because it seems like depending on, if my data is really high dimensional and actually varies independently in all those dimensions, then I can get some very, very large distances between points, and even a small change in those distances may be significant proportionally.
Well, yeah, so it really depends on the application, I guess, whether a 1 plus or minus epsilon guarantee is useful for what you're doing or not. So this all comes down to whether you want to, this is the guarantee you want or not. Yeah.
Can you say something about population level guarantees?
That's another good point. We haven't mentioned anything about a population. This is just, in fact, I could have made these x's small x's. These are just any n given points. I'm not even assuming they're drawn from a distribution. The only randomness I'm going to talk about is in the algorithm. So this is true for any point cloud. Doesn't matter whether they're drawn from a distribution or whatever. In fact, let me actually now state what the theorem says, which is that if I do this projection, then this statement here is true over the randomness of the procedure, which means constructing the matrix, with probability at least 1 minus e to the minus m epsilon squared over 16. Or I've expressed that in terms of m, but because m is bigger than this, another way to write this, which might be clearer, is 1 minus 1 over n squared. And you could imagine, again, maybe doing this twice and trying to get the best result. If you do this several times, you could maybe improve it. So you can think of lots of possible improvements. But this is just going to be the most basic version of the technique. So with very high probability, and this is for all pairs of points in your data set, no matter how they were generated. So let's prove this. And we'll just jump right into it, because the proof is not very difficult. What we really want to preserve, if I divide everything here by the norm of xi minus xj and divide that everywhere. So this is like 1 minus epsilon and 1 plus epsilon, and this is this norm divided by the original norm. So it's the ratio of the norms that I want to control. So what we really want to do is say something about this ratio. Somehow we want this to be close to 1. And what is this? This is just s times x divided by root m. So this is equal to s this is the matrix x multiplying, let's do this, xj minus xi squared over m. Oh, I'm sorry. I want to compare this to 1. Okay, that's what we want to say is that this quantity is small. I want to say this is close to 1. So this is s xj minus xi squared. It's s over root m, so that becomes m. This is our quantity of interest. And I'm going to rewrite that as 1 minus, I already have a typo. Sorry, it shouldn't be a 1. Just 1 over m, yes. 1 over m times, let's call it zi squared. This is a norm squared, so it's just a sum of something, right? So it's the sum, where zi is just this thing. It's the inner product. Let's call it SI. So let's write S is this matrix. Let's call the ith row S sub I. So it's the inner product of S sub I with this difference, normalized difference. And if I take this inner product, I'm taking the ith row of this times that difference there, and then I'm squaring it. That gives me this norm, this sum. And here's the 1 over m out front, and there's the denominator. So just writing it this way, we can see, somehow I want to say this is concentrating around 1. All right. Now, what is this zi? Well, again, it's this. We're thinking of the data as fixed here. This is just some vector, some fixed vector. We're taking the inner product with the ith row. I'm just multiplying it. Each row is just a bunch of normal 0, 1s. So when I take the inner product, I'm just taking a sum of normal 0, 1s. What is that? That's a normal. Mean is 0, and the variance, well, because the variance would be this squared, but I've divided by this, so it's normal 0, 1. So by construction, this is normal 0, 1. Just a linear combination of normals, so it's a normal. And by the way, you don't have to use normal projection matrices. People use other things, Rademacher variables, other things too. So again, this is only one version. All right. But we want zi squared, so what is zi squared then? What distribution is zi squared? Chi-squared 1. So we're summing up m chi-squareds. So we know that the mean of a chi-squared is 1. So this is looking good. This has mean 1, so the mean of this whole thing is 0. So far, so good. Now, we know when we do concentration of measure, we're going to do some sort of Chernoff trick. We're going to want a moment generating function. We're going to take e to, we're going to end up taking e to this whole thing, actually. So it will be helpful for us to remind ourselves what is the, when I do concentration measure, I can say the probability that this is bigger than epsilon, and I'm going to do the usual trick, the Chernoff trick. I'm going to multiply it by a constant and raise it, to take e to that thing, right? So I'm going to have to compute the expected value of e to this times some number. Let's start off by remembering what's the moment generating function. This is probably not something you keep in your head, but the moment generating function for a chi-squared 1, say m of lambda. In fact, I don't remember what it is either. I have to look. Yeah, I always forget where the 2 goes. So for lambda less than a half, that's what the moment generating function is for a chi-squared 1. So that's a useful fact. And I actually am going to need to know what is the expected value of e to the lambda zi squared minus 1. This term is going to come up in a minute, so let's compute it now. Well, I can see I have e to the minus lambda, and then what's left is, what is this part? That's the moment generating function for a chi-squared. And if you do a Taylor expansion of this, you can check, just go out to 2 terms is enough. You'll see that it's less than, make sure that matches with that, yes. Why am I doing this? Because I'm going to need this quantity in a second, okay? And if I take the product of this across all the data, in other words, if I look at the expected value of e to the lambda. Well, these are independent. So the expected value of E of this is just the product of these. So this is less than E to the 2m lambda squared. This is all just preparation again for when we Chernoff eyes the whole thing. You can see why it was convenient to pick a normal matrix, just because for one thing, it makes these calculations easy. But you can also see we could have done this with other matrices, matrices as well. Okay, with that preparation, let's actually do the calculation we want, which is to say that this thing is close to 1. So let's use the concentration kind of calculation that we've done many times, which is, I want to say the probability that that quantity, 1 over m, remember, if this thing was 0, then those two norms would be, the ratio of those two norms would be exactly the same, so that ratio minus 1 would be 0. So we want to see what's the probability that this deviates from 0. The probability that this is bigger than epsilon. So now I'm going to do the Chernoff trick. I'm going to multiply by a positive constant lambda, and then take E of both sides. So that's equal to the probability that I have lambda times 1 over m sum of r squared minus 1 bigger than E to the... Now I just do Markov's inequality. That's less than or equal to 1 over this. And we're left with the expected value of this, which, of course, is what we just computed over here. That was why we did that. So that's E to the... And now, as usual, we have a variational parameter, lambda, that we get to pick. This was true for any lambda. Okay, so if I pick lambda, I think the minimizer is epsilon over 4. This gives me E to the, this gives me, this gives me E to the minus m epsilon squared over 8. It all looks just like kind of like Hoeffding's inequality, that kind of argument. Now I only did one side. I have to do the other side, but by symmetry it's the same. So the probability that 1 over m zi squared minus 1 absolute value is bigger than epsilon is just less than 2 times that. It's just less than 2 times E to the minus. Very straightforward. But if you just plug in what this means, it's, well, let's go back to, it's that thing, right? It's the probability that the distorted, or projected, I should say, data, their norm is this. And if I divide that through by the probability that that's more than epsilon away from 1, we've just shown is less than or equal to 2e to the minus m epsilon squared over 8. So we're almost done except for one thing. That was for a particular pair, xi, xj. But I said this is true for all xi and xj. So how do I get that this probability holds for all xi and xj? Just do the union bound. So the probability that this is bigger than epsilon for some pair, for some I, is less than or equal to the number of pairs. The number of pairs is, well, it's n choose 2. At most n squared, right? So it's at most 2n squared e to the minus n epsilon squared over 8. But this is much slower than an exponential, so this is less than 2e, actually less than e m epsilon squared over 16. Which is what we claimed. As long as there's an n here, an e to the n, what happened to it? I used the fact, this is where we use the fact that m is bigger than log 32 log n over epsilon squared. That guarantees that this is sufficiently small to kill off that term. So it's really just Chernoff and the union bound over all pairs of points. Very, very elegant, simple argument. Yeah.
Is the dependency on Usum tight?
Is this tight? I believe it is. I think you can show there exist configurations of points that could never be reduced smaller than this with fewer dimensions. I'm 95% sure that's true. But this is assuming no structure on the data. This is just arbitrary pairs of data. In fact, we're going to talk about what happens when there's a little bit of structure next. So this is this is a fairly, I would say it's surprising, and it's very elegant. But it's only useful if this m is small enough that you've done a significant dimension reduction. Okay, any questions?
Yeah, I missed your motivation for doing this again.
Well, suppose you have a million dimensional data. You're doing classification, and you want to save time. You don't want to store this 1 million feature matrix. And suppose all your algorithms depend on, and I should say I'm preserving pairwise norms. You can also show you're preserving by similar argument inner products and things like that too. So if your algorithms only depend on norms and products, then this is saying you can reduce it down to dimension m, which must be much smaller with not too much of a distortion of all the norms, of all the pairwise distances and inner products.
Sorry, maybe I'm forgetting, but is there a similar guarantee with PCA? Or
No, PCA and MDS are quite different. All that, let's say MDS, because we know it's the same as PCA. What MDS does is it says, if I say I want I want to project my data into 5-dimensional dimensions, which projection minimizes this minus the projected distances summed over all the data points? It says nothing about how big that is. And it says nothing about it being, and it's about the sum of the distances, not about each particular distance. This is about every single pair of distances. And it says quantitatively how far away they are. They're 1 plus or minus epsilon. So there's slightly different guarantees. They're both working with the idea that pairwise distances are somehow what matters to you. If that's not true, then this is not a useful technique. But they're giving different guarantees. This is saying this is the best of all k-dimensional reductions, but it's not saying how good it is. This one is saying, no, I'm going to guarantee every pair I've preserved these distances to within 1 plus or minus epsilon. So a slightly different guarantee.
So suppose we use this to learn some algorithm which does depend on pairwise distances, but how does it behave on a different...
That's a really good question. So now you have work to do still. If you really want to say, okay, suppose somebody hands me data, and that's not the original data, it's these projected data, and I only know the pairwise distances are accurate to within 1 plus or minus. How does that affect that procedure? That's a procedure-specific question. And so you would need to now analyze, if you really being careful about it, you want to analyze how much does that affect my classification error or regression error, whatever it is that I'm doing. In fact, it might be bad in some cases, so it really depends on the application. In fact, I want to say a little bit about that right now. There's an effort to generalize this right now, which is I'd say it's work in progress because it doesn't necessarily work well in all cases, but there's a general way to compute these quantities. This is actually a special case of something more general called a Gaussian width, which is a new thing we'll learn about right now in terms of concentration of measure. And I'm not going to go through all the different results about it. I wanted to show you the technique, and then you'll see this is a special case of another technique. And then if you want to see once you've worked it out, and in fact, that question, how much does it affect my algorithm? There's a nice series of lectures by Martin Wainwright that he gave in the Netherlands. I don't know. If you type Martin Wainwright lectures Netherlands, I'm sure it'll come up because somebody scribed the notes while he was giving the lectures. And that's what his lectures are about, is what if you do this? The first few lectures just kind of review this, but then he says, what if you do this for least squares, for this, for that? And it turns out the story's pretty interesting. Depending on what algorithm you need to do, you might need to do something which is more accurate than this. You might need to do some further post-processing and so on. In fact, I'm going to talk a little bit about that right now. But before even asking that, let's just ask, if I wanted to preserve something else, something more general, how do I do this calculation? And there's a very, very beautiful result that allows you to do this more generally. Because look at that, look what the quantity is that we're preserving. That thing minus 1, right? So another way to write that is, what we were really doing is we were looking at the maximum over all pairs. I'm going to write this now as the sup of all u in k. Script k. I'm going to define k for you in a minute. Let's call this gamma of k. S squared over m, where k is just all those pairs. K is the set of all xi minus xj over their norm for I not equal to j. Right? If I just define, let's call this u, then there are n squared such vectors u. And so I'm just rewriting the thing that we just controlled, which was the probability that the maximum of this is bigger than epsilon. We were just controlling this quantity. And what do we know about this u? They all lie on the unit sphere, right? The norm of this quantity, by definition, if I take the norm, because I've divided through this, it has norm 1. So what we're really doing is, if you just think about it abstractly, I'm taking the unit sphere, and I've picked out n squared points on the unit sphere. They happen to be the differences of my original data points. Now just think of them as vectors on the unit sphere. And what I've really said is, I want to look at applying this matrix to a vector on the unit sphere, normalized, and take the maximum of them, in this case there's n squared of them, and say, what's the probability that this quantity is big? And when you look at it that way, you realize, well, there could be other quantities of that form that I might want to control. And so there's a lot, this is what the theory of sketching, it's called, is about, is given some subset of the unit sphere, it might be a more interesting or complicated subset. If I look at this distortion, gamma, what's the probability that it's bigger than epsilon? Or another way to say it is, how do I have to choose the resulting dimension m to make sure that it's small? Just to give you, let's look at two other examples of looking over the different subsets of the unit sphere. All right. One idea is I might take k to be the entire sphere. So this sphere I should call like SD minus 1 because it's the skin of the sphere, actually. It's the things of norm 1 that we're talking about, the things along this thing. So I'm writing it as SD minus 1 because even though this is in 2 dimensions, it's really a one-dimensional object. But instead of taking these n squared things, suppose I wanted to preserve every vector. Why would I want to do that? Well, because let's think of something that we often do. Well, let's write it. I'll follow my notes. Which is, if you think about what does a covariance matrix look like? Let's suppose I'm computing the sample covariance matrix. Suppose I've subtracted off x bar. It kind of looks something like a matrix transpose times a matrix, right? That's what a sample covariance matrix looks like. It's some matrix of data. Again, pretend I've already subtracted off x bar. So it's just S transpose S. In fact, if my data, this is M, if my data were normal, you could think of each, I can just think of S, instead of being like a random projection, think for a moment that I actually just have a data set, M observations, each one of length D. Maybe I'm getting my, or is it the other way around? And yeah, and then I want to know, let's suppose for the moment that this was drawn from a distribution with mean 0 and identity covariance. Then I just want to show you that this quantity reduces to something we might be interested in. Because if I put this in, in this case, I'm saying, let's take K to be the set of all vectors on the sphere. Suppose we make that choice. Because here here I'm just taking it to be some arbitrary subset. After rewriting it, I can just unpack this. This is just the inner product of SU with SU. So what do I get? And I'm going to pull out the M. So I get U transpose 1 over M S transpose S minus I U. Let me just convince you that's correct. If I look at this one, U transpose U, these are unit vectors, so that's a 1. And U transpose S transpose times SU is just the inner product of SU with itself, which is just SU squared. So I've just rewritten this. But the point is that if I now think of these, if this just happens to be not data I've done for projecting, but just a data set, then this is just my sample covariance matrix. And as I said, let's pretend for the moment that this is drawn from something with mean 0 and identity matrix, identity covariance matrix. What I'm looking at is the maximum. Should have this here. That's what is that? That's the spectral norm of the sample covariance matrix. We'll come back to this in more detail. This is very sketchy what I just did. We're going to do it in great detail. That's the next topic, the random matrix theory. I just wanted to show you if I change the set script K, we can get other things of interest. Not just pairwise distances. We can get covariance matrices. Sorry?
What can you get in this? Do you write it in this form?
Well, I just showed you one. We just did the pairwise distances was of this form. Covariance matrices of this form. But you can create other things. So for example, you might, suppose you're interested in doing, here's a very interesting one. Suppose I want to do least squares. But suppose you're Google and you've got oodles of data. And now they probably have very clever ways of distributing computing and so on. But you might think, if n is huge, this is a difficult thing to try to minimize. Maybe I could try to minimize. Maybe I could multiply everything by this matrix. That would reduce the size. That would just make my calculations faster, right? I've just now reduced it, the size of the calculation I have to do. But what is it I'd want to preserve here? Well, what do we know about the least squares solution? It's things that lie in the column space of the X matrix. So we might want to say, can I preserve things in the unit sphere that lie in the column space, such that U is equal to, say, X times V for some V. This is the design matrix. Should really be a design matrix for some vector V. We know the solution of least squares lies in the column space. It's, we're looking at things when we do regression of the form X times V. We're multiplying X by some vector. So you might, maybe if we can show that we could control pairwise distances of vectors of this form, perhaps we can show that if I did least squares on this reduced problem, it would approximate this. This gets to the question you asked about, if I do preserve pairwise distances in this space, does it imply that my least square solution is accurate? Unfortunately, the answer is no. However, it turns out if you iterate this, if you do this random projection, then do a regression, then do another random projection, and you do that several times, it actually does work. You actually, in the end, you can prove that you save the amount of calculations you have to do, but you can still approximate the least squares solution. And there's many, many calculations of this form. Here I'm just trying to motivate why we might be interested in this quantity. And it's just that whenever we take this dimension reduction technique of multiplying by a projection matrix, say a normal projection matrix, usually one first step in doing the analysis, and it may not be the last step, but a first step is to at least show that we've controlled this quantity over some interesting subset of the unit sphere. And obviously this is going to be harder to do the bigger k is. So in Johnson-Lindenstrauss, this was a finite set with n squared elements in it. But for various things, maybe you're doing matrix completion, maybe you're doing PCA, maybe you're doing something much more complicated, this might be a bigger subset. Okay? But it just raises the question. The concentration of measure problem we solved was, what is the probability that this is bigger than epsilon when I took k to be this particular subset of the unit sphere? Now I want to show you that if I take an arbitrary subset of the unit sphere, we get a similar result. I just want to tell you what the result is. Okay, so forgetting the motivation, now we can just think of it as an interesting concentration of measure problem, which is I take some subset of the unit sphere, k, and I multiply s times u, and I want this to be close to 1 with high probability. Given an arbitrary subset of the unit sphere, how can I possibly do that? Because when I did it for Johnson and Lindenstrauss, I did it for each pair separately and then took the union bound. But if this is a complicated set, like, oh, I don't know, I'm doing the lasso, and this might involve something about least squares. In order to make sure the lasso works, I might have to ensure that pairwise distances are preserved for certain things related to the column space of X and certain sparsity constraints. It could be a pretty complicated subset of the unit sphere. However it is, there's a very nice general result. I'm not sure actually who was the first one to prove this result. I've forgotten the history. Okay, and I'm going to tell you what the result is. We're not going to prove it, although the proof is not that much different from what we did for Johnson-Lindenstrauss. It's a little bit more complicated. It's a little bit more involved, as you might expect in general. But the flavor of the proof is still the same. But here's the result, and it's going to involve a new thing that we haven't defined yet. The probability that gamma of script k is bigger than something, and I'm going to write down what this something is. Actually, let's say bigger than, let's actually make this 8 delta. Is less than the probability that this is bigger than 8 delta is very small. As long as the key was the key in Johnson-Lindenstrauss was we had to pick m sufficiently large. And how big did we have to pick it? Well, it depended on log n. In other words, it depended somehow on the cardinality of this set. But if this is an infinite set, we can't use cardinality. And it turns out the right thing to use, in some sense, mathematically, is this thing. Actually, why don't I call this epsilon? I don't know why I switched to delta there. And I haven't defined w for you. I'm going to define w for you in 1 second. But let me just point out, this is exactly the same as the Johnson-Lindenstrauss theorem. So what is the probability that that quantity was bigger than epsilon, in this case 8 times epsilon? We want that to be small as long as the dimension we're projecting into is sufficiently large. And this, what is this projection? Well, this turned out to be like log n in Johnson-Lindenstrauss. But now what I'm claiming is log n is really a special case of something else. This thing is a very fundamental quantity. We've never defined it before. It's called the Gaussian width, and it's very much like a Rademacher complexity. It's simply the expected value of the sup of u over k of u times z. Whoops. Where z is just a standard normal random vector. So remember how we defined Rademacher complexity was you took these plus or minus ones, you imagine this random sequence of plus minus ones, you took the maximum of that and you took the expected value, and that defines some measure of complexity. This is very similar, except it's using Gaussians. You take any point u in your set, so that's some point u and k, and you take its inner product with a standard normal vector. Now you maximize that over the set k. So this is going to get bigger as k gets bigger. You take the mean of this, so that's some number. That's called the Gaussian width. It's very similar to like covering numbers and Rademacher complexity. It's another measure of complexity. And that tells you how big the dimension reduction has to be. Now, the reason why Martin gave like a sequence of 10 lectures on this is because the devil's in the details. For every problem you want to solve, you have to figure out, first of all, which subset of the unit sphere do I want to make sure the distances are preserved so that my algorithm later on will work well. That may not be obvious. And once I do that, how do I compute the Gaussian width? It usually involves things like covering numbers and so on, just like when we did all that concentration and measure stuff. But somehow you need to be able to compute this or at least bound it. And the third question is, when you find out, so if I did this in least squares, if I now said, suppose I want to do least squares and I want to reduce the number of observations I have to deal with, you can show that if you define k properly and you preserve the pairwise distances on that space, then sure enough, you can show that the least squares solution will be pretty accurate. Unfortunately, when you do that and you compute the width, you find out that m has to be of order n, which is the original data size. You haven't saved anything. So sometimes, that's why I said it doesn't always work, but then fortunately, you can often think of iterative versions or modified versions which will work. So that's why there's now this whole industry of people writing papers about sketching, because getting it to work in different problems may be non-obvious. But at least we know in the simplest case, the Johnson-Lindenstrauss case, it works. Right? There's nothing else to do except to do the projection.
Sorry, why is order n bad in high dimensions?
Well, because our original data set when we were trying to do least squares, it's already of order n. That's the original data set. So our hope was to, if I had 10 billion data points, the hope was to somehow reduce that and still preserve the solution, get approximately the right solution.
Can you show the Gaussian width on the previous example?
Yes, so what is the Gaussian width? Well, when k is finite, we actually solved this in 705. What is the maximum? What is the maximum? So what is the size of this? There's n squared points here. This is really asking what is the expected value of the largest maximum of capital N Gaussians? The sup becomes a max. Do you remember we did this? We said for anything that's Gaussian or sub-Gaussian, the expected value of the max is less than or equal to the square root of 2 times the log of the number of objects. Right? That was a theorem we proved. But this is n squared, so this is less than or equal to 4 log n. And so if I take that number and square it, I get log n over epsilon squared. We get back Johnson-Lindenstrauss. So Johnson-Lindenstrauss is actually a very special case of this more general theory. In fact, I did put a reference to one of this paper by Palanchi and Wainwright, which is called the iterative Hessian sketch, which does it it does not only least squares, but least squares with constraints, like when we put regularization on. And you'll see the paper is a little bit more complicated than what I've done here because of the fact that one random projection doesn't do it. It doesn't preserve it well enough. You have to do random projection, then something else, then another random projection. It's iterative, as the name implies. And you have to be very careful when you work in this area, by the way, to make sure you have to count how many operations your procedure takes. Because if after all this dimension reduction, if you haven't saved any computing time or memory or something like that, if it's just as bad as doing the original problem, then you haven't gained anything. Fortunately, they showed this does actually save you either time or memory. I don't remember which one. Probably time. Okay, so yes?
Do you think Gaussian test matrix is the optimal way for sketching?
Oh, is Gaussian? Actually, that's a good question. I don't know. There's probably a literature about what are the optimal sketches. I'm not familiar with it. I would think you can probably do better computationally because I know people try to come up with sparse matrices so that it's much easier to deal with them. In terms of statistical efficiency, I'd be surprised if you could beat it, but I'm not sure. But people do use other things besides Gaussians. Gaussian is kind of the simplest case, but there's work on using other distributions as well. In fact, there's some work by a guy by the name of Ping Li who shows, in fact, that you need to use thicker tail distributions if you want to preserve different norms, for example, other than L2 norms. It's a very, very big area. And so I wanted to do one example in full detail, which is Johnson-Lindenstrauss, and then just give you a flavor of what you're going to be seeing if you want to look up papers in the literature. You're going to see stuff about these Gaussian widths. And this is all it is. It's really just an attempt to generalize this type of result. So it's very interesting, an active area. And that finishes what I wanted to say about dimension reduction. So now we need to make a strategy decision. The next two topics, presumably the last two topics, are random matrix theory. In a sense, we've just done a little bit of random matrix theory. We're just going to go into it in a little bit more detail. And differential privacy. They're two unrelated topics that I thought would be nice to finish with. Now, given that there's always a chance that I won't get through both of them, I don't know how it's going to go. I don't know. Does anybody have a preference for which one you'd like me to do first? So I have a higher chance of getting it through. Adam? Unfortunately, there aren't. So the random matrix theory I managed to type in and post it. Differential privacy is still in my handwritten notes. I have, for the first time in the course, failed to get it into LaTeX at this point. So yeah, there's no notes for differential privacy. So I don't know if maybe you could have no preference at all. Maybe you don't know what either one of them is. Maybe you do care. So for those of you who care, maybe we should have a vote. And if you don't vote, I'll assume you just don't care. Who would like to do random matrix theory first? In Jisoo, you don't get to vote. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, how about differential privacy? 1, 2, 3, 4, 5, 6, 7. Pretty close, but looks like it's looking like random matrix theory is winning. Okay, I think we might be able to get to both. We'll see how it goes. So random matrix theory is an area that's also getting a lot of attention lately. I picked random matrix theory and differential privacy partly because they're both kind of hot areas. Now, it is a huge topic, so I can only just give you the kind of a flavor of what it's all about. These notes I based on some sources you can get on the web. So one of them is called Introduction to Non-Asymptotic Analysis of Random Matrices by Roman Vershinin. And the other one is Error Bounds of Random Matrix Approximation by Gittins and Trope. Terry Tao, who has an amazing blog, he actually has a whole blog post called topics in, it's a series of blog posts, topics in matrix theory, which he talks about a lot of this stuff. So you can find a lot of this stuff very easily online. What is it we're going to try to do, though? I want to be very focused here, and we're going to have a very specific goal, although the techniques we're going to talk about apply to lots and lots of problems. But to keep things focused, I'm going to say we want to answer one specific question. So I have x1 to xn are drawn from some distribution. These are vectors, so each xi is an RD. And I'm interested in estimating the covariance matrix. So I'm going to use the sample covariance matrix, and we're really just going to try to answer one question. How close is sigma hat to sigma? We've answered that question for like point estimators and vectors and so on, throughout 705 and throughout this course. But now we're dealing with something different. It's a matrix. And as we talked about a couple lectures ago, the difference here I'm interested in is going to be in the operator norm. If I was interested in the maximum difference between each entry, we're done. Because for any particular entry in the matrix, I could just use, say, Hoeffding's inequality or something like that, and then take the union bound over all the matrix. But we're not interested in that. I want to show that sigma hat is close to sigma in the operator norm. I'll remind you what the operator norm is, but the key thing about the operator norm is it is in some sense considered the more informative norm when we're talking about matrices, because in particular, if this is close to this in operator norm, it means, for example, that the eigenvalues of this will be close to this. And as long as the eigenvalues have a gap, it means the eigenvectors of this are close to the eigenvectors of this, and so on. So it's more about, the matrix norm is taking into account the structure of the matrix, the fact that a matrix is an operator, actually. And just to simplify things throughout, I'm going to assume the mean is 0. It doesn't matter. We could just subtract off the mean. Similarly, I'll take x bar to be 0. I know that seems a bit funny, but I can always subtract off x bar everywhere. That has this very small effect compared to the effects we're talking about. So we're going to just take all the means to be 0. So in other words, I'm just going to write sigma hat to be 1 over n xi transpose. Otherwise, I have to keep track of this minus x bar everywhere. And again, it's a lower order term compared to what we're analyzing here. And I'm going to rewrite this as 1 over n A transpose A, where A is just the data matrix. So this is just each. I didn't want to call it x because I don't want to confuse it with the random variable. So this is, in other words, this is x1, this is x2, this is xn, this is an n by d matrix. Each row is one observation. It's n by d.
Oh, A transpose.
Yeah. People have different conventions. In statistics, we always put each observation in one row. So it's always n number of people by d number of features. I know other fields do it differently, so it doesn't matter which way you do it, as long as you're consistent. But I'll try to be consistent and do it this way. All right. So the whole goal is just to show again that this is close to this, and I'm going to show you some pretty cool tricks that basically just build on our toolbox of concentration of measure. I'm going to mostly concentrate on the case where d could be large, but it has to be less than n. When d is bigger than n, we need completely different tools. Because when d is bigger than n, first of all, this isn't even invertible, for one thing, and we're going to need to talk about inverses and stuff like that. But also, this is not going to be a good estimator, generally speaking, when d is bigger than n. We're going to have to do other stuff. Okay, you need, in order to, just like for regression, right? For the high dimensional case, it was a different story. We needed regularization and things like this. So I'm just going to talk about the d less than n case, which is already pretty interesting. Okay, so before I plunge into the main theorem and the proof, we need a little bit of background, which will just be a review, I hope, for you, but some notation from linear algebra. So, first of all, this matrix A, this is just a data matrix. So this is not symmetric, it's not square. But remember, it has an SVD, a singular value decomposition. Let me remind you about that. The singular values of this matrix, we'll call them S1, S2, down to SD. These are just the square roots of the eigenvalues of A transpose A. And just like we have a spectral decomposition for covariance matrices, for the original data matrix, we don't have quite the same decomposition. We have the singular value decomposition, which looks like this. It's U, D, V transpose. So let's get this right. This is n by d. This is n by d. U, did I put these down yet? U should be n by n. And V hopefully is d by d. There we go. So let's make sure that's right. Yeah, that's n by d. And that's d by d. That's n by d. This is a diagonal matrix with the singular values. And U and V are orthogonal matrices. Basically, the columns of U are the eigenvectors for AA transpose. The columns of V are eigenvalues for A transpose A. So, you know, for a symmetric positive definite matrix, U and V are the same. Here they're different because this is not a square matrix. All right, so what's the spectral norm of a general matrix? The spectral norm or operator norm or operator norm. The norm of A, and there's lots of different notation here. So some people write this, some people write A op. There's all kinds of different notation. I'll just, if I put the norm there and it's a matrix inside, just assume it's the spectral norm. It's just, it turns out, well, and when I put a vector, if I don't say what kind of norm it is, it's always the L2 norm. So it's simply this. And keep in mind, this is a matrix, this is a vector, this is a vector, so this is the ordinary L2 norm, and it's the sup of this. It's not hard to show this is actually just the largest singular value. There's another way to write this. Since this is review, I'm not going to show any of these things. But you can show that this can be written in the following way, and this turns out to be important for proving things, which is this is the the way to prove this is if you just take a clever choice of V here, you'll see you get the same thing. That if I take AU times V and take the max, this is the variational representation of the operator norm, where U is varying in this unit sphere and V is varying in this unit sphere. So this actually looks less useful, right? I mean, this looks pretty clean and everything like that. But for proving things, it's going to be easier actually to use this equivalent version, as we'll see. Ultimately, what we're going to do, probably have to do on Thursday, is use a covering argument. We're going to cover the spheres with, we know they're covering numbers, so we can cover them, and we can approximate this max with a finite max instead of taking the maximum over the whole sphere. So that's why I'm writing that down. And you can check in the special case for a d by d symmetric matrix. This all reduces to the way we defined norm before. The norm of this squared is just its first singular value squared, or if you prefer, it's the first eigenvalue of B transpose B, or the max of U equals to 1 of just A times U squared. So this is all just reminding you of stuff. I think you know this. If you don't, it's all here for you to look back at if you forget anything. A few other facts we need before we start anything is remember that the action of the matrix on a vector is controlled by its singular values. If I take A times any x, that's bounded above and below by the largest singular value of the matrix times x and the smallest one. In particular, if I can show that the singular value of a matrix, if the biggest one and the smallest one are close, then this is almost an isometry, length-preserving matrix. In fact, that's what we're going to show. What we're going to show is the following theorem, that root n, with high probability the following is true. For some constant c, root n minus some constant times root d is less than sd is less than s1 is less than root n plus c times root d. This is the way it's usually written, but this is the singular values of the original matrix A. If I divide A by 1 over root n, what are we interested in? We're eventually interested in this thing, which is 1 over root n A times 1 over root n A, because this is our estimate of the covariance matrix. So we're really interested in A over root n. So if I divide through here everything by root n, this is going to look much more interesting. This will call now the smallest singular value of 1 over n times root A. So look what we've got. We've got that the biggest and smallest singular values are 1 minus, and as long as d, again, is not big relative to n, hopefully this is small, and similarly here. So this is both close to 1. From this, it will be easy to show that sigma hat is close to sigma in operator norm. Why? To make that even more explicit, I'm stating a lemma, another standard lemma from linear algebra. This is now, if you have the notes, it's lemma 1 on page 2, which just says in symbols what I just said in words. If I have a d by d symmetric matrix, so think of this like covariance matrix, for example, then if B transpose B minus I in operator norm is less than, actually let's focus on small delta. Well, yeah, let's focus on small deltas. So if that's less than delta, then the smallest and biggest singular values are between 1 minus delta and 1 plus delta. The notes have a more general expression because I'm allowing for large delta, but we're really interested in small delta. And essentially the reverse is true too, up to constants, up to some constant 3. Okay, so what I'm trying to say is that showing that this is close to this, and let's imagine we're going to start with the case where the true covariance matrix is identity. We'll do the more general case in a minute or later. Suppose we're starting with the general case where the special case where the covariance matrix is identity. Think of this as the sample covariance matrix. We're saying this is close in operator norm, that is, this is less than delta, implies that the biggest and smallest singular values don't stray too far from 1, and the reverse is true too. If these are not too far from 1, that implies this is true. That's the link between getting control of the singular values so you can see over here, this is the delta. This is why this is not going to work for high-dimensional matrix theory. And if I think, let's again think about the case where we have mean 0 and population covariance matrix identity, and take B to be 1 over root n A, then this is nothing other than sigma hat, and this is nothing other than sigma. And what we're trying to prove is that this is small, that this is less than delta, or epsilon, whatever you want to call a small number. The point is that controlling that the singular values, the biggest and smallest, are trapped between 1 plus or minus something, and saying that these are close to an operator norm are also it's essentially the same statement. But what would happen if sigma was not I? So I'm going to do all the calculations assuming sigma's I, but you think, well, that's not very useful because sigma's obviously not I. But if we can do the case where the true covariance matrix is I, we can do the general case. Let me show you why. It's because of the following. So what we're going to do, suppose that the covariance matrix now is some general matrix sigma. And let me define Wi to be sigma to the minus a half xi. In other words, xi, I can always write as sigma to the 1/2 Wi. But of course, Wi now has a covariance matrix, which is the identity. And if I put these w's in a matrix, you can see, it might seem weird, but you have to multiply it the other way, just because of the way matrix multiplication works. If I put all the w's into a matrix, let's call it this funny font W, then at a matrix level, what I'm saying is the original matrix is W times this. The reason why it's on the right-hand side is to make sure it's multiplying each row of the matrix. That's the same. That's because when I write xi, that's really a row of the original data matrix. OK, so watch what happens. I'm interested in the operator norm of this. But this is A transpose A, which is just W times sigma. So this is sigma to the 1/2 times 1 over n W transpose W minus I all I've done here is, you can check now that I've got sigma to the half, sigma to the half, a W, put that in, and you're going to get back A transpose A over n. And of course, this becomes sigma to the half times I becomes sigma. So I've just decomposed it like that. And now I can use the fact that that's less than or equal to the norm of this times the norm of this times the norm of this. And in fact, the norm of this, the norm of sigma to the half times the norm of sigma half, it's easy to check, is just the norm of sigma. So this is less than or equal to the operator norm of sigma times the operator norm of 1 over the rescaled data Did that make sense? All I'm doing is rescaling the data. The distance of this from this in operator norm is now the distance of the sphered data. This is called the sphered data, compared to its identity. This is the true covariance of this. If I confused you, just all I'm doing is, if x has variance sigma squared, then x over sigma has variance 1. That's all I'm saying. Okay? This has variance 1. And if I've made this less than epsilon, then this is just some number times epsilon. Assuming this has a finite norm, of course, otherwise none of this makes sense. So what I'm saying is there's no loss of generality in assuming that the data we're dealing with have true covariance identity. Because if it doesn't, we just do this trick. We just rescale it. We divide through by sigma to make it have norm, to make it have covariance identity, prove that that converges, and then we just end up using this inequality. So that's why I'm going to, throughout the calculation, just assume that the true covariance is the identity covariance. And again, for simplicity, that the true mean is 0. It's not hard to show. It still holds, even if the mean is not 0. All right, so we're almost ready to prove what we want to prove, which is something like this is small with high probability. And as usual, this gives me a chance to show you a couple more tricks that we haven't done so far. Here are two lemmas that you can add to your bag of concentration of measure tricks that are actually good to know about. We're not going to prove them. The proofs are, especially one of them is actually quite a little bit long, but they're very, very, very useful things to know. And if I had done this when we had done concentration of measure, it would have been useless because we wouldn't have used it till the end of the course. So I didn't mention them then. Okay, the first one actually is lemma 3. This is a really cool thing. Suppose I have a random vector, which is standard normal. And suppose I wanted to make a concentration, a tail probability result about x. We know how to do that for normals. But suppose I'm interested in a function of the normals. Let f, let's say x is in, let's say this is d by d. And let f map rd into r. How does f of x behave in its tails? Does it have normal-like behavior? The answer is, if it's Lipschitz, it does. So suppose that this is a Lipschitz function. Then the following theorem is true. I'm not sure if this is named after anyone. The probability that f of x minus its mean is bigger than t is less than or equal to e to the t squared over 2k squared. In other words, the normal tail-like behavior is preserved. This is actually a pretty amazing theorem. Because other than being Lipschitz smooth, this is an arbitrary function. But it is making use of the fact that we're starting with a Gaussian. It's not for an arbitrary thing. It's not like McDermott, where we started with some arbitrary thing and said, what happens when I perturb it? This is starting with a Gaussian. But the result's very beautiful. It says as long as you take a sufficiently smooth function, we still get normal tails. So we're going to make use of this result. And there's one other result that we're going to use, which I'll just state now. I'll remind you of this on Thursday. This is another very, very important theorem of probability. It's called the Fernique inequality, or the Sudakov-Fernique inequality. Let me just state what it is. And it might seem like when I write this down, you're thinking, how is he going to use this in the proof? But you're going to see we're going to need this. Remember that we had, we talked about Gaussian processes at some point. What is that? That's some random function whose any finite number of coordinates are Gaussian. So if I have two mean zero Gaussian processes, but suppose that one of them is smoother than the other one. So suppose that for any point s and t, the expected value of x sub s minus x sub t is smaller So what is this saying? It says that x is wiggling around less than y. Then intuitively, you would probably think the maximum of y would be bigger than the maximum of x, right? It's true. If this holds for all s and t, then the mean of this process is less than or equal to the mean of this process. So y, sorry. This is very intuitive. if I have a process which is kind of smooth, another one which is wild, this is going to be bigger than this, and you'd expect this to have a bigger maximum. But it's non-trivial to prove this. Okay, so this is it's one of those things that seems intuitively true, but it takes quite a clever proof. We're just going to take it as given that a more wiggly process or a more variable process will have a higher mean than this process. Okay, and it's what we're going to see on Thursday is using these two new results plus some results that we're already familiar with, like using covering numbers and things like that, that we can prove that we can control the singular values of a random matrix. Again, restricting ourselves to the case where d is less than n. So I went a bit long because I still have to give back your tests, I guess. I'm sorry about that. We'll finish this on Thursday, and if there's time, I'll do differential privacy. And in the meantime, let me give you back your... So you know that I failed at... I thought by making the test similar enough to the practice test, it would be really easy. Apparently it wasn't.